All right, IBAISL2. We're going to start today talking about the third dimension. We're talking about 3D solids. You may have seen some of these solids before, but we're going to go over everything from a pretty fresh perspective. First up, prisms. Prisms are these shapes that have the same congruent shape on either end and then are just connected by parallel lines. So a triangular prism has a triangle on one end and then a triangle on the other end. And then those are connected by three parallel lines. You can have lots of different types of prisms. Like this is a hexagonal prism because there's a hexagon on one side, a six-sided polygon, the honeycomb, and a hexagon on the other side, and then it's connected by six lines to create the hexagon. Now, technically, a cylinder is a prism. It's just a prism that has a circular base. So here's a circle on one end and a circle on the other, and then it's connected by, well, it's kind of wrapped with a rectangle around it is how I think of a prism. Yeah, so in your homework problems in 2F or 2E, they ask you to sketch some things. One of them might be a prism with like certain ends on it. We're also going to talk today about pyramids. So the base of a pyramid is a polygon, which means it's like a shape with straight sides that's on the bottom. In a right pyramid, the apex is vertically above the center of the base. Here's what they mean by that. The apex is like the very top of the pyramid, the pointy part, and that, if it's a right pyramid, is directly above the base. It's not like off to the side or something like that, because if it was off to the side, it'd be like a slanty pyramid, or a non-right pyramid, I guess is how we would say that. Not every pyramid is going to have a triangular base. Just like the prisms, you can have pyramids with different bases. So this one has a rectangular base, or kind of looks square, but I'm not going to assume. This one has a triangular base. Now, triangular pyramids have a special name, which is called a tetrahedron. It's the four-sided shape. You can have lots of different bases on your pyramids, but another one might be like a hexagonal base. So here I see a hexagon, and then it's all, all the vertices of the hexagon connect up to the apex of the pyramid up here at the top. Cones are kind of like a pyramid, just the same way that like a cylinder is sort of like a prism. I mean, it is a prism with like a circular base. A cone is a pyramid with a circular base. So you can have cones where there's a circle on the bottom, and then this is the height. They don't call this the apex, they call it the vertex for some reason. And then the slant height is the edge of the cone. Some other things that might come up are spheres, which are just a perfect 3D circle, or like a ball or a planet. And then a hemisphere is one half of a sphere. It's like, the top or the bottom. Well, it's a sphere cut in half. Okay, let's actually do some problems now that we have some vocab. Cuboid, A, B, C, D, E, F, G, H. So cuboid is just another funny word for like a rectangular prism. I realize it has that word cube in it, but it's not a perfect cube. It doesn't have all sides the same. It's just like, it's made of rectangles. It's a 3D rectangle where every side is a different rectangle. Or it doesn't have to be different, it just is a rectangle. So the sides are 4, 5, and 6. We're going to find the length of diagonal DF. So if I highlight DF, it goes from the front left corner to the back right corner. So in order to figure out what DF is, I think I'm going to need some extra pieces. DF is part of this triangle right here, where this is a right angle. Now I know this side is 6, but I don't know what this side on the base is. But if I draw the base on its own, and this is a good strategy with these problems, if the diagrams get too confusing, you can redraw parts of it to see what you know and what you don't know. So here's what I know about the base, and we're looking for that part DB. Since it's a rectangular base, I can use Pythagorean Theorem to figure out what DB is. So we do 4 squared plus 5 squared equals dB squared. 16 plus 25. Brain's not working today. 41. So the square root of 41 is equal to dB. So in my diagram, this is root 41, but also over here, that's the square root of 41. Then in this big triangle, it's another right triangle. I know two sides and I'm trying to find the hypotenuse. So I can use another Pythagorean theorem to say that square root of 41 squared plus 6 squared is equal to df squared. 41 plus 36 is 77. So this is the square root of 77 is equal to df. So this was all part A, finding df. Then it says find the size of Bdf. Well, if I trace the angle BDF, maybe I should use a different color. B to D to F. That's not a great color for this diagram. How about red? That's this angle right here. Now, that's part of a right triangle. So here, I can do, like, I just said we can always redraw things. I think that's a good strategy if the diagram starts getting too messy, and put in what you know. So we know this side is 6, this is square root of 41, and then we found that this side is the square root of 77. And we're looking for this angle right here, theta. Because it's a right triangle, I can use Sohcahtoa. So I'm going to do sine equals opposite over hypotenuse. So sine of theta equals 6 over root 77. Then theta is going to be the sine inverse of 6 over root 77. Make sure your calculator's in degree mode. 6 divided by square root 77. 43.138. See if the book agrees. Yep. 43.14 degrees. So BDF 43.14 degrees. There's that old problem. Next up, another cuboid with dimensions 4, 5, and 6 as shown, but M and N are midpoints of D, H, and BF. So if those are midpoints, I'm going to remind myself by putting little congruency markings over here that this is the same as this, and then this is the same as this. Actually, you know what? If like the sides are 6, if the whole thing is 6, then we know each of those is 3. I bet that's going to come up. Find angle NEM. Well, the first thing I notice is that triangle NEM is not necessarily a right triangle. So, even though it looks like a right triangle, I don't think you can assume that it is, because it's like cutting through a weird part of the cuboid. I think if it was more aligned with two sides, where two sides were met at 90 degrees, like I don't think you can say that this side and this side meet at 90 degrees. So, within that triangle, let's get rid of some of those markings. I know that MN is going to be the same as DB. Like if you had a light directly above it, that would be the shadow would fall directly on DB. So let's find DB using the Pythagorean Theorem, because in the base rectangle, there would be a 90-degree angle right here within this triangle. So dB squared is equal to a squared plus b squared. So that's root 41. So, because that's root 41, its partner up here is also root 41. Now, if I look within just this triangle right here, I know that this side is 3, because that's half of the 6 side, because n is a midpoint of FB or BF, and that because this side is parallel to this side, that this is a 5. Looked like a 6, 5. So I can use Pythagorean Theorem again to try to figure out what En is. So En squared is going to be 3 squared plus 5 squared. 25 plus 9 is 34, so we get square root of 34 is that side. Okay, I got 2 sides in that triangle, but let's go ahead and go for the third side. Within this triangle right here, first of all, it's a right triangle because that side is a rectangle. This is 3, and this is 4 because it's parallel to this side right here. 3 squared plus 4 squared equals 5 squared. That's a nice Pythagorean triplet. When you 16 plus 9 is 25, and the square root of 25 is 5. That's called a Pythagorean triplet when they work out nicely like that. Now I have all 3 sides of triangle MNE. Because I have 3 sides and I'm trying to find angle NEM, which is this angle right here, I can use law of cosines. So, square root of 41 squared is equal to 5 squared plus root 34 squared minus 2 times 5 times root 34 times the cosine of angle NEM. All right, let's play a whole bunch of cleanup here. Squares and square roots cancel each other out. Then, let's see, 41 take away 25 take away 34 is going to be negative 18. So I'm just subtracting these two from the opposite side. And that's equal to negative 10 root 34 cosine NEM. Now I need to divide both sides by this coefficient. No need to decimalize that. We're just going to keep it all as exact as we can. Then I have to do an inverse cosine. Also, these two negatives cancel each other out, so I'll just go ahead and get rid of those. Cosine to the negative 1, 18 over 10 root 34. So you have to punch that all into your calculator. And then round to the nearest 2 decimal points. I believe that's 72 degrees. All right, that's that whole problem. Last one, a rectangular pyramid has a base with dimensions 8 and 5 and a vertical height of 10. It's all in the diagram. That's nice that they're giving us a diagram. O is the center of the base and is directly below the apex E. Find the size of the angle. So we're finding angles in all of these. Between the edge BE, so locate BE, and the base of the pyramid. So the edge BE is this right here. And then we want the angle with the base. So they're talking about this angle right here. I'm noticing that this is part of a right triangle, where I know the height is 10, but I don't know what this side is right here. if I redraw the base of this pyramid, there's a cross that goes through the middle. And this is O. This is B, D, C, A. I know that these are sides of 5 and 8. So my goal is to find this little chunk right here, but that's half of CB, and CB is in a right triangle because this bottom is a rectangle. So with Pythagorean Theorem, CB squared is equal to 5 squared plus 8 squared. 64 plus 25 is 89. So this is the square root of 89. But then that's the entire side of CB, and I want OB, which is half of that, because the diagonals of a rectangle bisect each other. So yeah, it's half of that. So OB is equal to root 89 over 2. Now if I go back over here, that means that this side, the height is 10, and this side is root 89 over 2. So in this right triangle, this is the opposite side and this is the adjacent side. So that means I need to use tangent. So to find the angle, this is all part of part A. I'm going to use tangent of, well, we can't really call it anything. Let's call it angle EBO. It's equal to opposite over adjacent. So then EBO is going to be equal to a tangent inverse of 10 over root 89 over 2. Which is about 64.7 degrees. Part B, find the angle between the edges EB and EC. Well, EB and EC, they're talking about this angle, here I'll use yellow, this angle right here up at the top. But if you picture this big triangle going from here to here and then across, that's just going to be double whatever this angle right here is. So if we can find this angle and double it, that'll give us the entire angle at the top. So for part B, I'm going to find, since I already know two sides in that triangle, I'm going to use Sohcahtoa to figure out what angle OEB is. So tangent of OEB is opposite over adjacent. Opposite side is root 89 over 2, and the adjacent side is 10. Oh, you know what? I'm doing too much right here. I mean, I could go this route, but if we look at this triangle right here, and when I say this triangle, like there's so many in there, I mean this guy, triangle EOB, we already figured out that this side, this angle right here is 64.7, and then this angle is 90. So we can just subtract those off of 180 to figure out what OEB is. So OEB is equal to 180 minus 90 minus 64.7 degrees, which is, here I'll do it. 180 minus 90 minus 64.7 is 25.3. But that's only half of the angle. We just found this guy right up here, and we want the full thing. So we need to double that. So 2 times 0.5.3 is 50.6. Yeah. That's part B. Part C, EMO, where M is the midpoint of AC. We're finding EMO. Use a different color. So that's E to M to O. Well, it's a right triangle. So if I know two sides, I can use Sohcahtoa. I already know that this side is 10. So let's just figure out maybe what MO is. I think that's a good way to go. OE and EM. So back in my original diagram over here, like this, we're looking for this side right here. In this smaller triangle that I'm highlighting in orange, this is 2.5. Here, I'll use a better color because that side gets split. And then this side gets split as well. So this is 4. This is a right angle. Oh, we just know it's 4. Yeah, duh. So that means this side is 4, OM. And then we can do, what are we finding? EMO? That's this angle right here. Call it theta. Okay, so for part C, it's getting messy. EMO is going to be tangent of EMO is going to be 10 over 4. Opposite over adjacent. Yeah. So then EMO is equal to tangent inverse of 10 over 4. And that is 59 degrees. All right, you guys, that's all I have for us today. We are splitting section 2.3 into 2 different days. So this is just part 1. We'll finish up 2.3 next class.